Finally, we can implement our chosen solution and solve the problem. Okay, so now we need to find the heat flux through each of our three layers. And to do this, we start with our equation for heat flux, which is just the Fourier's law, which just says that Q equals minus the thermal conductivity times the change in temperature over the length. And we can use this relationship to find the heat flux through our frozen layer, our protecting material, and our good tissue. So let's start with our frozen layer, or our tissue to be destroyed. So Q frozen, the heat flux in the frozen layer is equal to negative the thermal conductivity of the frozen layer times the change in temperature, which is just the temperature at 1 centimeter minus the temperature at 0 centimeters. So write that in. Divided by the length, which is just the length of the tissue to be destroyed, which is just our 1 centimeter. And we could do the same process to find the heat flux through the protecting material and the good tissue. And once we have three equations for each of the heat fluxes, because we determined that the layers are in series, we know that these three equations are equal to each other. So we can set them equal to each other and solve for any unknowns that we have. Okay, so now we have our flux for the frozen layer, or the tissue to be destroyed. We have the flux through the protective layer, and the flux through the unfrozen layer, or the good tissue, that we need to protect. So as we determined earlier, we need to set these equal to each other to solve for any unknowns we have. So once we plug in our known values, we can see that we have two unknowns, this K protect and this temperature at 1 centimeter. And we also notice that if we set this equation equal to this equation, and say this equation equal to this equation, we have two different equations and two different unknowns, so we can solve for our unknowns. Okay, so now let's solve for the temperature at 1 centimeter. If we equate the first flux with the third flux, we can solve for our temperature at 1 centimeter. And we end up getting our temperature at 1 centimeter as minus 190.8 degrees Celsius. Finally, using our temperature at 1 degree Celsius, we can equate the second flux with the third flux to solve for our thermal conductivity of the protective layer. And in the end, we determined that the thermal conductivity necessary is 0.0535 watts per meter Kelvin.